This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 2301 statics. We're reviewing a recent test. We've got a problem involving vectors in 3 dimensions. Now you'll see here's the setup. I've got 3 vectors, F1, Cartesian, F2, just given the direction angles over here, alpha, beta, gamma. F3 is a Cartesian format also. So the goal of this is a lot of times just going to be to get your forces in Cartesian format so I can manipulate them easier. The first problem was to determine the unit vector in the direction of F3. Okay, unit vector is a pure direction vector. And so I just need to get the scalar magnitude of F3, which is down here in green, which is the square root of the sum of the squares of its components, 130. So U3, the unit vector in that direction, is equal to 40I plus 120J minus 30K over 130. So I just do the math and I get 4/13 I, 12/13 J, and negative 3/13 K. That's the answer to problem number 1. Remember, a unit vector is just a pure direction, and it always should have components of 1 or less, some fraction usually, unless it's just a pure I, J, or K unit vector. Part 2 was direction angles, alpha, beta, gamma, of F1. Here's F1. I need to get, it's kind of like this up here. We'll take it a step further. I need to get the scalar value of F1, which is the square root of the sum of the squares, 170. Then I get a unit vector, and those are the direction cosines. So just divide 170 into these components, and I get 0I, because I have 0I in the force vector, plus 150 over 170, or 15/17 J, plus 880 over 170, or 8/17 K. So I just take the inverse cosine of these numbers. The inverse cosine of 0 is 90 degrees. It gives me alpha. Inverse cosine of 15/17 is 28.1 degrees. And the inverse cosine of gamma is 16. Gamma is the inverse cosine of 8/17, 61.9 degrees. That's the answer to number 2. Number 3, express F2 as a Cartesian. So it's kind of the backwards reverse of this problem. I'm given the direction angles, which is what I solved for here. Now I want to work backwards. So I say that the unit vector in the direction of F2 is the cosine of the direction angles, cosine of alpha, cosine of beta, cosine of gamma. Here's my alpha, beta, gamma. Plug those in here. Cosine of each one of those is 0.5I minus 0.5J plus 0.707K. Now I need to convert that into force vector, which is just multiplying the scalar value of F2 by the unit vector U2. 200 times all those components gives me 100I minus 100J plus 141K pounds. This is one where we had one answer, just those components and no unit. Hope you didn't fall for that. The second answer, another choice was involving pounds, but the same number. Number 4, the dot product of F1 and F2. So it's F1 dotted with F2, but up here I've got them in Cartesian format, which helps me. This is F1, 0, 150, and 80. F2 is 100, negative 100, and 141 from up there, right above it. So remember, in a dot product, I'm just multiplying the x components times each other, y and z components all times each other. 0 times 100, 150 times negative 100, 80 times 141. Do the math. I get this. I got a negative there. I got to keep track of my negatives. It's everything with respect to its sign. It's negative 3690 pounds squared. That shows what an abstract thing dot product is. What is a pound squared? Number 5, magnitude of the projection of F1 in the direction of F2. Okay, I've talked about translating English into vectors, vector language. Projection should make you think dot product. Direction should make you think unit vector. So what this means is magnitude of projection. Oh, magnitude also means scalar. I didn't write that down, but a dot product is a scalar. So it's F1 dotted with U3. The direction of F3 is U3, unit vector 3. So here's F1 expressed as Cartesian. Notice that I've put a 0 as a sort of a placeholder there in front of it in the I position. And I dot that with unit vector U3, which I've got from way up here. Do the math. 0 times 4/13, 0, 150 times 12/13, 80 times negative 3/13. Multiply it all out. I get 120 pounds. And part number 6, question number 6 from this whole setup is angle between F2 and F3. If I use the words angle between in English, that means dot product in vector. That's kind of the way you need to look at it. So that's F2 dotted with F3. And then I'm going to use this relationship. F2 dotted with F3 is equal to the scalar F2 times scalar F3 cosine of theta, the angle between them. So I just say the scalar values. I'm going to work part of the problem here is 200 times 130 times the cosine of that angle. So it's 26,000 cosine of the angle. Now I need to use the other way I can evaluate a dot product, which is multiply the x, y, and z's together. And so I say F2 dot F3 as vectors is the x is 400 times 40, negative 100 times 120, 141 times negative 30. Evaluate that out. Remember, this is a scalar, just adding up numbers. I get this, negative 12,230. So the cosine of theta is equal to one way of evaluating it, and then I divide by F2 and F3 multiplied together, which I've got from up here. Remember, I got to keep that negative sign up there. That's important. Negative 0.4704. So theta is the cosine inverse of that, 118 degrees.